Hello everyone, allow me to introduce myself. My name is Aditya Kurniawan and I'm doing the research with multiple institutions. Uh, for example, the Polytechnic Kota Malang, my college, the other college is from UIN Sunan Gunung Jati, Pak Eki Ahmad Zaki Hamidi, and from Polytechnic Kota Malang is Ibu Kholilatul Wardani. And I'm doing this research with the title Simcom A7600c1 LTE module for intelligence and real-time precision maintenance schedulers on a Volvo inline T16C610 engine. So this is the outline of my presentations. I purposely will do these presentations for approximately 15 minutes, maybe 15 minutes is the maximum. So the first one is I will do the introductions, and the second one is I'll be talking about the Volvo engine overview, how it works and why it is important to do the research on Volvo engines. Number 3 is maintenance process and parameters on a coal mine hauling, because different industry in coal mine haulings do different maintenance process and different parameters. And the fourth is the improvements for maintenance process using intelligence and real-time precision maintenance, and this is what the research is about. And the next is about the modules, or Simcom as data communication modules. So this data communication module, we install it and we implement it on a real F816 unit of Volvo prime mover. That the pictures is on the right. So, and the last of the presentations will talk about the results of this research and projects. Next, so this is how the site area works. So this is how it works. You can see the red dots over there. Here I'll move my pointers. So the red dots here is the coal mine or intermediate coal facility. So it stores the coal that is created by the industry, the mining industry. So this is just like a big storage. So the units, just like this, it has a double vessel arrangement. It will drag the coal about 280 tons from this point, the red dot, and it will go 70 kilometers ahead to the tipping point, which is the yellow dot. And the distance between the loading point, the red dot, and the green dot is about 70 kilometers. And the trip that is done by the unit, so the unit has to move from the red dots, the intermediate coal facilities or the loading point, to the tipping point, about 70 kilometers, and it has to do this trip about 3 or 4 trips a day. So what makes that become a problem? The engine is actually a mechanical devices, so it has a lot of mechanical contacts. So inside, if you can see here in these pictures, it has, for example, a camshaft bearings, camshaft pulley and piston ring. So all of this device, when the engine is running, is like rotating, and it keeps like crossing one another. For example, this cam lobe. So the cam lobe will cross, or will make the metal here weary. So it's a wear metal. Uh, so it is connected by the camshaft here. It has a double camshaft, so it has a double shaft with a cam lobe. And here we have a crankshaft and the connecting rod. So actually, if we talk about the wear, the metal wear of the engine, we talk about how many rotations that it has made. So it doesn't matter if you have if you make the engine running about 2 hours or 3 hours. It doesn't really matter, because what really matters is how many rotations the engine or the crankshaft has done. So that's why, by doing this trip, for example 4 trips a day with the distance 500 kilometers a day, the hour meters we just will only record 18 hours a day. And in coal mine industry, the hour meters is used for the parameters, for the maintenance parameters. So if we use this hour meters, which is 18 hours a day, it actually does not match with the engine wear rates, because if you push the full throttle of the engine, for example 1000 rpm, and if you push the throttle in a low rpm, for example 100s, it make a very big difference if you let the engine running for an hour. If you push the full throttle for 1000 rpms, it means that you have a 60,000 rotations for this engine. But if you just do a low idle, for example 100 rpms in this engine for an hour, then you only have 6,000 rotations. So compare with the full throttle 60,000 rotations, and low idle means it's a low throttle 6,000 rotations. It makes a big difference on the engine wear. So if you calculate using the hours, it does not match with the engine wear. In this scenario, in this research, we try to make the parameters better than just using the hour meters. And this is the Volvo engines. So the Volvo engines, inside the Volvo engines is installed what we call with magnetic pickup sensor. So the sensor will read the RPM of the engine, so how many rotations the engine has made, and this engine speed. For example, this one, you can read it through the dashboard. So you have to connect this dashboard with the laptop, with your computers and adapters from the Volvo Tech Tools, and then you can read this engine speed in RPM. So this value is actually what we're looking for. So in the next in this research, we try to pick up this data of engine speed, and we try to send it wirelessly using the Simcom modules. So this is how it works, the maintenance process and parameters before the implementations of this research is the industry is using the hour meters, which is showed here in these vehicles or in these engines. You can see the engine hours is 20,724. It means that the engine has been running for 20,000 hours regardless of the RPM it has made. I mean, if you pull the full throttle or the medium throttle or the low idle, it doesn't matter. The engine hour is just counting how many hours the engine is running. The other is, this is the input of the maintenance process, and the process is by using the schedules, and then you do the maintenance by the hours. For example, the periodic service 250, periodic service 500 hours, periodic service 1000 hours, and so on. So by using this data, the mechanics will do the periodic service based on the hours of the engine. The output for the maintenance process is MTBF, or mean time between failures. It means that it shows you how many hours the unit has been running without any failure. And the other is by taking the sample of the oil of the engine. So for example, this one has an attention status. It means the engine is in danger situations because of the unmatched because of the running hours is actually unmatched with the wear of the metals inside the engine. So this is the improvement that we have made. We are creating a simple programs. So the hour meters will be calculated by this formula, and we added a simple module inside. So the hour meter now is reading differently. For example, if you run the engine 1000 hours or 1 hour, you run the engine 1 hour and you let the engine running in 1500 RPMs, then the hour meter will read only 1 hour. But if you pull the full throttle, for example, and let the engine running in 3000 RPM, then the hour meters will read 2, even though the engine is actually running in 1 hour, but the reading will read 2. And by this scenario, using this scenario, it will let the maintenance hour or the maintenance schedules done before the maintenance schedule done correctly. So that is how the improvement works. We just try to replace the parameters before. So before the research, the implementation of the research, they use this hour meters, and now they use this new parameters, which is the converted hour meters, which is directly taken from the RPM of the engine and from the sensor of the engine, and sent directly to the phone by using a apps, and we develop it using Blink apps like this. So this is the Simcom as a data communication module. We install it here. This is inside the Volvo FH16 prime mover. The cable here, we unplug it and we put a new modules using the node MCU here, and we take the sample of the data of the engine RPM and we fed it and we send it wirelessly using Simcom A7600c1 LTE modules, and using the RTC as the real-time clock. It will send the data of the RPMs to the maintenance schedulers every 1 hour. So in 24 hours we have 24 data of RPM, the RPM and the hours. So the hours before will be corrected by the RPM of the engine, because before it doesn't, the hour meters doesn't really calculate the RPM of the engine. Now using these modules, the hour meters is calculating, also calculating the RPM of the engine. So how does it works is like this. First we start it, and then the RTC will count 60 seconds. If it is not 60 seconds yet, and update the RTC, and if the RTC is already 60 seconds, then the CPS and AUTS data available. If that's available, then Node MCU will read the data and send the data to Blink Cloud database, and which is created in using the Blink apps. The sample of the print screen apps is here. So after 1 month using this scenario, the value for MTBF, or the mean time between failure, is getting better, about 1.8 hours. It means that the unit is broken down rarely than before. And in a period of a month, in January 2022, the engine oil unit for PM 829 that we implement this research has spent 100% of its total running hours in normal status, because the month before the unit is running with the attention status, means that the engine is in danger, but now is in normal status compared to the year 2021. The engine oil analysis results is it means that it is in healthier conditions after the implementations of this research. The summary is the revised prototype has been installed and tried in a real-world environments and has been proved to raise the value for MTBF about 1.8 hours. And the status change, the oil sample status changed from mostly attentions to normal due to the change of the oil is now happen more frequent whenever the unit runs the engine faster than the recommended cruising speed, which is 1500 RPM given by the factory. So that is the suggestions, and the next projects we probably will try to detect the engine wear components further, so that the hour meter value could represent the real engine wear is to implement by implementing the engine load parameters in the real time. So that is my presentations, and the end of my presentations. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.